Bluetooth. Get it straight.
Okay, let's look at one more problem from Chapter 8, and this is a problem where we're looking at turbulent flow, and we're going to have to use the Moody diagram or the Holbrook equation, and iterations will be required here. So we've got a water tower, and it's 80 feet high between the top of the water and the water tower, and the pipe down below, and got a gate valve at the opening of the pipe, and the pipe is 600 feet long. So it's old pipe, 20-year-old cast iron pipe, and you'll see why that's important in a minute. The gate valve has a KL. That's the head loss coefficient, or the friction coefficient for the gate valve. From the table there is 0.15. It's fully open. So these pipe problems usually involve Bernoulli. And remember, so we have our Bernoulli terms as usual. And then we've got our major and our minor head losses. The major one is for the pipe, and the minor one is for any fittings in the pipe. So if we look at this, we should say that the top of the water in the water tank is at atmospheric, so that's a 0. The velocity at the top is also 0 if it's a small amount of flow relative to the big size of the tank. The Z is definitely not 0 because that's the height up there, 80 feet. Down at the other end, again, we have an open pipe coming out, so it's a pressure of 0. We can say that the bottom of the system is the datum, so that Z2 would be 0, but there's definitely going to be some velocity coming out of that pipe, so this one here is not 0. And of course, we've got the major and the minor head losses. So if we simplify this, we can see that we would get 80 feet, which is Z1 is equal to V squared over 2G times 1 plus the major head loss of the pipe, which is F over LD. Remember, major head loss is F over LD times V squared over 2G. And then the head loss for the valve, which is our only fitting, probably would have a elbow in here, but we're not given any information about it. We'd probably have the inlet here, but again, we're not given much information. So all we have is the open valve, and that KL is given. And remember that KL times V squared over 2G would be the head loss for that pipe. So we just usually have terms that look like this, where we have 1 plus some friction term times L over D plus any number of KLs, but in this case we just have 1. So the key point of these types of problems that tell you need iterations is that we don't really know what V2 is, and we need V2 in order to get the Reynolds number so that we can get a friction factor, so that we can get these this head loss from the major head loss. So we're stuck there. So we have to do some first trials and then circle back and try it again. So let's get started on that one. So we have cast iron pipe. We can look at the table, and we see that its E is 0.00085 inches. And then for old pipe, kind of the rule of thumb here is that we multiply that by 2 because it gets even rougher, especially with this iron. It gets corroded and pitted, so there'll be very high roughness. So that means that epsilon over D, the thing we need to get into the Moody diagram, is 0.000425. We know that means we'd enter the Moody chart on the right-hand side at 0.000425, but we wouldn't know where to stop. So the first time in, we're just going to assume that we use the wholly turbulent line, which is kind of the approximation of the turbulence for a fully turbulent case. And you see what I mean when I go down to the chart. So it's this dashed line that's associated with the wholly turbulent flow. And so if we take ourselves to about 0.000425, right around here, and we go over to the dashed line, kind of parallelized with the 0.004 line, we get about right here, which would take us down, or would take us over to somewhere around 0.016, right about here. Didn't draw that very well. So if we have that 0.016 back up here, and approximately that. We know everything that we need to know because this was the only thing we're missing, F term. We know all these other terms, and we plug it in, and we'll get our first estimate. So notice I've got subscript here, V2 sub 1. That means it's our first iteration, says it's about 12.3 feet per second. So if we plug that in for Reynolds, we would get a Reynolds number of 3.1 times 10 to the 5th. Now we go back to the MoodyChart because that's not going to be directly under what we just connected with. See, we connected over here, so that would take us down here. But instead, we're going to be over here at about 3.4 times 10 to the 5th. And we take that up to 0.0425. This curve is up a little more. And that's going to take us over to a different F. So we'll call this F1. And here's F1, here's F1, F2. So we just circle back and we try that. Now you can see I've changed my subscript, so I have V2 sub 2. I've got a new F2 that's slightly bigger than my last F2. Plug that one in, I get 11.5 feet per second. So you see the velocity came down. Plug that 11.5 in, I get a new Reynolds number, Reynolds sub 2. I go back to the Moody like I did before, and you can see here that the F sub 3 is 0.018. Before it was 0.0185, so things are not changing very much. And you can keep going, but basically, once you get a little bit smaller changes, less than about 2% or so, you're not going to improve the answer too much. And it's probably within the uncertainty of how well you're pulling off the numbers on those curves. So eventually I say, okay, that's good enough. And I put V2 sub 3 in here, and I get the velocity of 11.66 feet per second. For flow, I get, just use the geometry of V2 times A2, I get 1.01 cubic feet per second. I translate that into gallons per minute just by units conversion. I get 455. So in the initial problem, forgot to mention that the fire department wants 500 gallons per minute. So the trick here is it's probably not going to work. So that's we want to find a Q in the fire department. It needs 500 gallons per minute. This would be pretty close. We would probably say this is not going to do it for them because it's on the low side.